Before attempting this problem, make sure you understand problem 28 in chapter 4. For part A, we basically have one big block moving to the left because of force F. So it's going to look something like this. Our free body diagram, what's touching the block? Force F is touching the block. The surface can interact two ways, through a normal force and through friction. And if the block is moving to the left, then we have kinetic friction to the right. And that's everything that's touching our block, and weight can reach in from a distance, or I should say gravity can reach in from a distance. So I'm going to select my positive direction to be to the right, to the left, in the direction the block is moving. Okay, it tells us it's moving at constant speed. And so what does that mean? That means the acceleration is going to be equal to 0. So just key words you need to pick up on when you're working these problems. Constant speed, acceleration is 0. So I have a vector equation, sum of the forces equals ma, and I break that up. Sum of the forces in my x direction and sum of the forces in my y direction. And I'll call this my x direction, and I'll call the perpendicular direction the y direction. So the sum of the forces in the x direction, I have a positive F, I have a negative friction, and that's all I have. The acceleration is going to be 0 in that direction. The sum of the forces in the y direction, I have a positive normal force, I have a negative weight, and those also sum to 0. There's no acceleration in that direction. And so I end up with F is equal to my friction force, and my normal force is equal to my weight, which is equal to mg. The friction force is mu times the normal force. So F is going to equal mu times m times g, and that's 0.3 times 1.2 newtons plus 3.6 newtons, which is 1.44 newtons. So our answer is in newtons. The direction is given in the problem. It's pulling the blocks to the left, and that's what's required to keep them moving at constant speed. Now the problem gets a little more interesting. We have block B being pulled and block A is tied to the wall. So let's draw our free body diagrams for blocks A and B. What's touching block A? Well, there's a tension in the rope, and there's a surface. It's touching the lower block, so that surface can interact with it in two ways: through a normal force and through friction. What direction would friction be in this case? As we move block B to the left, the friction force is actually going to try to pull block A to the left. So we have a kinetic friction force on A from B. And thus everything that touches block A, and then we have gravity reaching in the weight of block A. On block B, things are a little more interesting. We have a force, F, acting on B. We have the bottom surface, right, the ground, acting on B. So it's pushing up with a normal force. I'll put from the table. We've got a couple of normal forces. So this is the normal force on A from B, normal force on B from the table. There's a friction force here. When we pull block B to the left, the friction between block B and the table is to the right. So there's a kinetic friction on B from the table. And block A is touching block B. So we have a normal force on B from A, and we have a friction force on B from A. I think that's everything that's touching block B. And something can reach in, the weight of gravity. So real quickly, let's take a look at Newton's pairs. We have a normal force on A from B and a normal force on B from A. So they are a Newton's pair. That means they have to have the same magnitude. We have a kinetic friction force on A from B. And we have a kinetic friction force on B from A. Those are a Newton's pair. Those are resulting from the same interaction. Okay. So what we want to do is write our equations. We say for block B, sum of the forces in the x direction are going to be 0, and the sum of the forces in the y direction are also going to be 0. And so I have F, that's my only positive force, and then the two friction forces are going to be in the negative direction. And my y direction tells me that the normal force on B from the table minus the normal force on B from A minus the weight of B has to be 0. And I just have to plug in some things here. My friction forces are mu times the normal force. And my normal force BT is the normal force BA plus the weight of B. So I'm going to plug this in over here, and I get F is equal to mu times the normal force AB plus mu times the normal force BA plus the weight of B. And then we know that the normal force AB and the normal force BA are all the same, and they are equal to the weight of A. So I'm going to make that substitution. and I end up with 0.3 times 2.4 plus 3.6. I end up with 1.8 newtons. So force units are in newtons. The direction is given in the problem, so I'm not going to restate that. It's to the left. And you can see from your free body diagrams, it gets a little complicated, but you can see that because if B was just rubbing on the ground, there'd be a friction force opposing that motion. But B is also rubbing against A, so that friction force also opposes the motion. So you have the two friction forces there. And then you have to sort of use Newton's third law to figure out that some of these magnitudes are the same.